John, how can you always have the right TV for the right application without carrying hundreds of valves on your truck?
You can carry the hundreds of valves on a trailer behind your truck.
That's too funny. That would work, but how are you going to do that? Maybe there's an easier way.
You can use Sporland's interchangeable cartridge style Type Q and Type BQ TEVs. Type Q is a conventional design and Type BQ is a balanced port TEV.
Well, come on. I need easy. How easy is it?
Easy as 1, 2, 3.
And it serves thousands of unique applications. So what's the process? How do I put this together?
First, you select the thermostatic element assembly. Then you select the body that you need. Then you select the right size cartridge for the application to get the proper capacity TEV for your application. And then I guess it should also be said you want to actually assemble those into a single valve.
That'd probably be a good idea.
Indeed.
These easy to select and assemble valves mean you're always carrying the right valve for the right job then. If folks want to learn more, what do they do?
You can go to sporland.com and find more information on the Type Q and BQ thermostatic expansion valves.
I guess that's Jim and John for Sporland signing off.
We've all been there, in the middle of a job, everything going smoothly, until boom, you're missing a part. United Refrigeration is your one-stop shop for all your refrigeration needs. Use your computer or smartphone to go to www.uri.com at any time of the day or night to check stock on your favorite brands, such as Copeland, Sporland, Carlisle Compressors, Danfoss, Emerson CPC boards and sensors, Carrel, Hussmann parts, and K2Therm. United Refrigeration Inc. is home to these brands and many more. Looking for information on refrigerant conversions or refrigerant banking? Quick access links on the homepage can get you to the information you need. All approved accounts are able to see live to-the-minute inventory and pricing. Product not in stock at your local branch? No problem. Use the Nearby Stock feature to find a local branch that does have what you need. Are you looking for a branch address, phone number, or after-hours number? That's all available as well. Just click on the branch locator and search for your local branch. Have a model number and looking for a replacement part? www.uri.com/ARP has a vast list of quick pick replacement parts. Just search for the model number of the equipment you're working on and click the Replacement Parts tab. If you don't have an account, click the Register button and we'll have you online in no time. With more than 400 locations in North America, each United Refrigeration branch is fully stocked for immediate pickup. Our branch employees have in-depth technical knowledge, so we can help you get what you need when you need it. Visit your local store or www.uri.com/ARP today. United Refrigeration Inc. has all your solutions down cold.
Good evening, everybody. Welcome to Advanced Refrigeration Podcast. You're here with your host, Brett Wetzel and Kevin Compass. Where are you at this week, buddy?
I am back in the lovely state of California, hopefully for the last time. And I doubt it too. My wife said the same thing. Yeah, I flew out here to help start up another CO2 rack, and because the manufacturer bailed on the startup, and basically just said they don't have anybody, so good luck. And so I ended up having to cancel some plans and cancel a job and come out here to start this up, and then it slowly devolved into a shit show like normally, and ended up a bunch of the coils that got installed were piped wrong from the manufacturer, had wrong valves in them. And
hold on, explain that. Explain just a little bit how they're mispiped.
So certain manufacturers, mostly one, Carnot, uses forward gas defrost. So instead of reverse gas defrost down the suction, they use forward gas defrost down the liquid line. So they inject the liquid line with hot gas, and that's how they defrost.
Via the liquid line, right?
Via the liquid line. So your liquid line sizing gets increased, and then your valve sizing is almost double to triple to sometimes 4 times the size it normally would need to be.
I'm assuming this is because of capacity for the expansion valve, right? Like
Yes,
just making
flow.
sure you have enough flow in order to warm that coil up. What gas are they using? Are they using legitimately hot gas, like coming from the discharge? And you know,
like below freezing hot gas.
so they're using the flash tank pressure. They're using gas vapor off the flash tank.
Off the low temp compressors. They're using vapor off the low temp compressors too. Yeah. So it's below freezing. I mean, it's a 20 degrees saturated condensing temperature. Technically, it's below freezing. It's just superheated. It's superheated below freezing gas.
So they're basically taking a lower saturated gas coming from the flash tank. And
no, not from the flash tank. Straight off the compressors.
Oh, I'm sorry. So straight off the discharge of the low temp compressor. So you get a little bit of sensible heat, but I don't know how to understand how that works too well, especially if you're giving it
It's
20 degree saturated gas.
like a slightly medium, less shitty cool gas. Like slightly. It's got a little more heat to it, but like doesn't want to move as much. So they're the only ones doing that. So the coils all got to get piped differently, and they need these huge, humongous valves. Like, for example, like Pederi cooler coil has an SERG in it. It would be fine with an SERB. Probably an SERA you could get away with. It has an SERG. It's
Isn't
like
a G like a 30-ton valve?
Oh yeah, it's like a 30, almost a 40-ton valve.
Okay.
So they don't use check valves or anything like that. So these coils came out piped with check valves and A valves in them. So, and unfortunately, nobody caught it, and you really couldn't check a size in the valves because I spent probably a half an hour in there with a mirror because Sporlan stamps them on the body. And unfortunately, this manufacturer shoved them in the coils, and it's like 10 inches from the coil door to the end of the U-bends where it was. And it was up against the U-bends on every single one. I was in there with a mirror and a light for like 10 minutes trying to get the valve sizing off of it. Couldn't see shit. So once we found that out, we were kind of dead in the water. Then the OEM screwed around and, hem-hawed about whose fault it was. I didn't really care. I just wanted the parts. So that didn't get started up. So on that today, we went through and fixed all the programming and fixed all the wiring and got all the compressors bump started and all the coils checked where the electricians miswired a bunch of stuff. So it's a long startup process, especially when you have remoted defrost panels and remoted like case controllers. There's a lot of wiring that's got to get checked. I mean, a lot less when it's cases. I mean, it's a lot easier to fly through cases and check them. I mean, I'm checking the suction line temp sensor and the pressure transducer. I don't have to worry about it being on a different case because it's one case, as I do with, there's a lot less error to be happening on cases than there is on, walk-in coils or stuff like that. Go ahead.
So I had a question. So obviously we got the below gas defrost, is the defrost time essentially increased on shit?
It's like 45 minutes for a freezer coil.
Really? Where typically you could do hot gas or cool gas and literally get it cleaned off in probably like 15 minutes, regardless
Correct.
if it's cool gas or cool gas or hot gas, right? And the other thing you said was that the coils were piped in improperly. So is this the particular not manufacturer, but is this the particular customer where you can either run like a 3 or 4 pipe header defrost system with regular HFO refrigerants, but because they're using the CO2, what's the deal that you said that they were piped incorrectly?
No, they're just the way the coils are circuited and laid out, like they do it differently.
Okay, I didn't know if it was one of those things like, I know Keep Right has a certain method of how they do. There's basically a big check valve assembly that comes all together, and I didn't know if it was something like that.
No, like these were supposed to be hot gas pans, but generally, when they do the hot gas pans with CO2, they just make the whole liquid line run through the pan. So the whole entire liquid line will run through the pan, and that's where your hot gas enters first. It enters the liquid line, so they'll make an entire loop through the pan, and then they'll run the out of there to the valve into the coil. So they just make their own pan loop, but without check valves and all that stuff.
So
So they just make their own pan loop.
does that mean you're going to be waiting on brand new evaporators now because they
No,
weren't?
because there's electric defrost heaters in there, and now obviously evaporators are going to take less time than wire to pull.
Rather than wait for the correct evaporators, right?
Correct. Which me personally, I would much rather have electric heaters for drain pans. I absolutely despise hot gas drain pans.
No, is
All they do
this
is leak, and they never get warm enough.
okay? Wow, that really sucks. Yeah, I got nothing for you.
I'm wrapping up and flying home tomorrow, so I'm stoked I get to go home early and take my kids to the fair. So at least there's that. At least something good came out of it.
Oh, I meant to ask you. I heard you had an interesting thing going on with your son. Tell me about that story.
We will not.
What? You're muted.
That's a negative there, Chief. That's a negative.
Come on, I was so excited.
Tonight. No, we're not talking about that. So tonight we're gonna talk about some basic stuff, guys. After Brett stops being a dick, we're gonna talk about defrost and types of defrost and like back to the basic stuff with defrost for some of the newer guys. So Brett, you want to hit it off?
Yeah. What are we trying to do when we defrost coils? Right, we're just trying to get all the ice and snow and anything that's adhering on those coils off. Right. Multitude of methods of different ways of defrosting. We have, sometimes in older Hellphoenix cases, you'll see reverse air defrost. That method is basically taking the normal flow of air, and there's typically a relay inside of the case. So whenever that relay is active, basically changes the air direction. So instead of the return, at the bottom of the case and the discharge air coming out the top of the honeycombs, it reverses it, pulls a little bit of air from outside of the case and runs it through the coil. And if you ever have one where it's no longer working, one of the things that you can do is just make it a regular off time defrost and make sure you pull that relay. There's typically a relay in there that switches the fan rotation from going to the left from going to the right. You do have to make sure every single fan motor is exactly the same. If you try to put a regular conventional motor in there with those 3-ported fan motors, it will not switch rotation. So keep that in mind. You also have off-time defrost, and with that, we really like to shut off the suction for that, because one, that helps with migration for refrigerant, and just it causes the pressure to increase a little bit faster because you are closing off the suction side. If no one's ever told you, obviously higher the pressure, higher the temperature. So the higher that we have the pressure in that suction, the faster that coil is going to heat up, right? And as Kevin said, we try to use gases that are above freezing, right, as far as the pressure temperature relationship. So that's why if you ever have a case of lineup that is fully de-iced up or frosted up, and you're trying to get it done or get it cleared as fast as humanly possible, one of my biggest things I like doing is shutting off the suction ball valve, shutting off the case, or shutting off the suction ball valve to the case, my bad, and just letting that liquid just continue to feed, because it's just going to keep feeding liquid. That pressure in the suction is going to start going up, and it will start defrosting that coil a lot faster. We also have hot gas, which is taking exactly what it sounds like. There's different methods to doing it. And usually HFC and HFO refrigerants, we're using a differential valve, whether it be on the liquid or the discharge side, and using that to create a differential. So when we put the refrigerant in the suction line, it's able to get back up into the liquid line, and that's how hot gas is done. Same thing with cool gas. The only difference is the supply of where we're getting the gas from. We're getting the gas typically with cool gas off of the top of the receiver. Some different manufacturers, they have different methods of cool gas. One method is I'm just going to call it the Hill Phoenix method of making cool gas. They have a little de-superheater. They run the hot gas through this, it looks like a big oversized T. Typically it's orange and blue and red. And so the hot gas going in gets de-superheated by a little bit of liquid feed off of the system. So just to bring that temperature down. The theory is that, if we bring the temperature down to, I don't know, I think usually the set point it's like 73 or 74 degree gas, because that's what they're doing. They're monitoring the gas temperature, and that's how they're making sure you get the proper amount of temperature. They're looking to not do a lot of expansion and contraction with that certain method. And sometimes with also, hot gas, they do, Kevin's method, what he's got going on. I think that's the one where they, they're causing a pressure difference across it. Like are they using ball valves to mitigate the pressure to get your flow, or how are they doing it on that rack you were working on?
So they have a discharge, like an inlet pressure regulator, an IPR valve on the discharge of the compressors after the oil separator, and it's before the takeoff it's after the takeoff of the hot gas line feeding the circuit. So they have like a discharge pressure regulator. They set it like 500 pounds. So, and then it flows backwards and dumps into the medium temp. It's not an accumulator, it's an intercooler. So it dumps into the intercooler. So it dumps that raw liquid straight to the intercooler coming back.
They don't try to reutilize it and repurpose it for, back to the flash tank at all?
No. So what they're doing is they dump it in the intercooler and send it out to the low temp cases, because the low temp liquid lines are the intercooler is feeding the low temp liquid header. So they're always keeping a level in the intercooler of like 15 to 20%. So the intercooler is basically your low temp receiver. So it's constantly keeping that liquid in there to recirculate around through the rest of the store, like an industrial ammonia system.
Gotcha.
So lot of stuff like that is, set up and do it. But I'll say it, cool gas defrost sucks. It's horrible. Should have been one of those things that died in the 90s.
Oh, stop.
It's terrible. You can't float your head real good with it. It barely works. In large applications, it doesn't work with a shit.
I still think it works fine.
Medium.
Well, I mean, your method where it's below saturated, I don't really dig. You know what I mean?
No, that doesn't work either. I'm talking raw hot gas. You can't beat 200 degree hot gas going to, thaw a coil in 5 minutes.
You sound like a boomer.
I'll take it. I'll take that boomer comment. Like, I mean, let's just be honest. Cool gas should have died a long time ago.
Stop.
So, and that Hill Phoenix method is witchcraft.
What do you mean?
That valve is witchcraft. I know how it works, but like after seeing one of those on a cooling tower, I was like just sold on those things. I seen one of those exact valves on a cooling tower on the drop leg, and it was literally de-superheating the discharge line to the point where you could just touch it.
I have a picture somewhere of the fucking valve cut open. I gotta find it. A good friend of mine, Ray Kelly, he's an engineer. The first time I ever met him, I'm like, "You actually have one of those valves?" He's like, "Yeah, it's cut apart over there," and like, it's literally a big copper T with a brass Venturi, welded in on the inside.
Yep, that's all it is. It's a Venturi orifice. That's it, and it works amazing. Like, I could not believe that it was dropping these racks in Las Vegas, Nevada, on a cooling tower. It was dropping the discharge lines to 70 degrees just off the weight of the liquid coming out of the cooling tower. It was dropping that discharge temp down to like 70 degrees.
I wonder
And
how
that is a huge increase on capacity on the cooling tower.
yeah, I wonder how much like you're potentially saving, or how much it actually costs for usage. You know what I mean? Because like obviously, if you're de-superheating discharge temperature from, you know, I don't know, 180, you know, down to 70 degrees going into that freaking thing.
But there's really no loss from compression. So
no, I'm not talking about that. I'm talking about the sheer, you know, amount of liquid that it would take from whatever refrigerant you're dealing with in order to, you know, to cool that.
I'm sure it's a lot, but at the end of the day, like, I mean, the capacity gains on the cooling tower alone would probably pay for it.
Yeah, probably.
I mean, if you're de-superheating 150 degrees and now 3/4 of that condenser coil is condensing, I'm surprised we don't see more air-cooled condensers with them. Apparently, I was told it was utilized more in cooling towers to keep them from scaling up.
Well, that makes sense. You know, that's the coffee pot method, right? You know, think about it that way, where, you know, when you have an old coffee pot that's had heated water in it for such a long time, you get that white film because you have all the particulates dropping out. So I guess it's the same fucking theory then.
Yeah, I mean, if it keeps the cooling tower from scaling up, I mean, on the upper tubes where most of these superheatings happen, I mean, let's be honest, look at most cooling towers. That's where they look like the shit more is on the top, not on the bottom where the subcooling's happening.
True. Very true.
So
you want to start with, you know, since we're talking about all defrost and all basic parts of defrost, you want to start first with just regular off time. We'll go from there.
So off time, guys, a lot of ways to accomplish it, but it's all the same in the end. So off time defrost, what are we doing? We're just turning off exactly what it says. We're just turning off the refrigeration, whether it's a compressor, a solenoid, an EPR, stepper valve, whatever it is, we are just turning off that application in order to defrost it. So, I mean, you could have a liquid line solenoid shutting off and pumping out, and it's timed off. It's for so many minutes or so many hours. That's how it's going through its defrost. You could have a EPR that is shutting and letting the pressure build up inside on the back pressure, like Brett said, letting that pressure build up and stack all that refrigerant in there to help defrost it. That could be doing it. It's driven off a computer. You could have a stepper valve shutting on the liquid or the suction. So you could have an EPR, or you could have a EEV or a pulse valve shutting, and that could be your off time defrost. And when it comes back on, it starts regulating again. You could be as simple as some single units in a mechanical room where all we're doing is shutting off the compressor and it's letting the pressure rise up, and we're in a mechanical room and we're far away from the cases. We're not going to flood back, just shutting off the compressor, letting it sit until the cases are defrosted. So off time defrost is generally controlled by a time clock or a EMS system, and it's going to go for so many minutes. And generally, you don't have termination on that. You can, if you have an EMS system, you could integrate termination on the discharge air temperature or coil temperature. But generally, if you're doing off-time defrost, most of the time it's just going to be termination off of discharge air temp, meaning case temp, or it's just going to be off for so many minutes. Say if it's a 40-minute defrost 6 times a day, it's going to shut off for 40 minutes 6 times a day, and whatever temperature it's at is going to come back on. So off-time defrost is generally for stuff with SSTs no lower than 20 degrees. Once you start getting saturated suction temperatures below 20 degrees, you start building frost more, that you're going to need some other method of defrosting, whether it be reverse, electric, or hot gas. So generally, those temperatures are reserved for that. And the closer the fin spacing, the more frost buildup you're going to get. So the more frequently you're going to need off-time defrost. So off-time defrost has a harder time thawing that coil every time than some other non-passive defrost would. So it is essentially free. No other heat gets added to it, but I mean, nothing's free in this world. So defrost still costs money, even though you're not adding heat to it, but the electric defrost or hot gas defrost, you still are adding BTUs to the rack when it comes back on and having to pull that product down. So still utilizing the proper defrost times and essentially spacing it out during the day is critical. And with off-time defrost, the intervals are just as critical as the lengths. I mean, if you have coils that are frosting up in between defrosts, it's not the length that's usually causing it with off time. It's the interval in between defrosts. You need to have a more frequent defrost. So if it's, see it trending warm after, 4 hours, it may need a defrost every 6 hours. I'm sorry, if it's every 6 hours and you see it trending warm, you may need to defrost every 4 hours, or you may need, more. Some of these new cases Kaiser has cases that are 18 times a day, which I about shit myself when I seen it.
Well, that's what I was just about to say. Like, you have to make sure you're going to the spec of whatever manufacturer. And like, I did the same damn thing. I did a triple take. I mean, because I have ADHD, so I'll read shit. And I'm like, oh, I forgot what it just said, and I'll go back. But like this time I was like, okay, it says 18. Wait, that's at 18. And I went back. I'm like, yeah, it says 18. I'm like, there's no fucking way it says 18. So actually, I spent the time on tech support just to call them. I'm like, just making sure that I'm not off my shit. But this is definitely 18 times a day. He's like, yep. I was like, when the hell does it run?
Well, yeah, and that's a huge issue because some EMS systems won't even let you put in 18 defrost a day. Yeah,
you end up having to do numbered or whatever. So where you pick a reference time.
Sometimes. Well, it won't even some stuff on the older E2s and won't even let you. It'll let you do 12 a day and that's it. And then in the RMCC, you can only do 6.
Even if you put numbered on there?
Yep.
Today's episode is sponsored by the Refrigeration RDP series differential pressure monitors from Westermeyer Industries, now available for transcritical CO2 systems in addition to other common pressures and refrigerants. When the filter element of your coalescing oil separator is contaminated, it can hurt your system's performance and efficiency. But how do you know when it's time to replace that filter? Wait too long to replace, and you could end up with a nasty filter blowout. But replacing too often can be a waste of time and money. The answer is installing a differential pressure monitor. The RDP series differential pressure monitors, including the new transcritical CO2 model, are available now from Westermeyer Industries. To find out more information, email sales@westermeyerin.com. That's WESTERMEYERIN.com.
Wow, how the hell would you deal with that?
You have to increase the time. So I was having to cook the cases, basically. I was having to get them up like 45. So say it was 20 minutes 6 times a day, or 18 minutes or 15 minutes. Now it's 45 minutes at the maximum time it can go. So, I mean, it has to get that coil more clear. It just had to deal with it. But yeah, that's a huge issue. In some controllers, like microthermals, max 12 times a day.
Oh, wow. Well, one of the things that you do have to make sure when dealing with, regular off-time defrost is that you're not getting any liquid generation, like, slamming out at you. And what I mean by that is, typically when you do have off-time defrost, you'll either have a liquid line solenoid, on a regular conventional case, or you will have a suction stop, with a liquid line solenoid. It's basically just stopping the flow of refrigerant entirely. Sometimes what can happen with rack systems, you'll have a case that's where the liquid line solenoid is continually feeding because it's not fully seated. So it ends up filling the whole entire line from the evaporator or from the liquid line solenoid all the way out into the evaporator, all the way back to the EPR that's at the rack. So you just have an abundant amount of liquid that just gets stowed out there during defrost. And then when it turns back on, all of a sudden, oh, I don't know, every day at 12 o'clock, I end up having a shit ton of flood back, which end up taking out my compressors. And like I said, it's you might not notice it at first, no erratic liquid level, because that'll happen too. Typically, if you have your liquid line solenoid feeding, not only is your liquid level going to change in your receiver, because you're basically filling up that whole line set and the whole coil with straight up liquid, but then on top of it, you have the suction that ends up dropping like a rock, because you just have so much liquid that then needs to get back to the rack, and the only way it's getting back is through the suction, and there's no controlling factor. It's just, as soon as that EPR opens up, whoosh, you can get all that liquid running up in. Typically you can find it with, like I said, utilizing the graphs to try to figure out when the suction temperature, takes a dump and goes all the way down to, where you're basically having liquid feed to your compressors. You got anything to add?
Yes. So on bigger stuff like warehouse type coils, big box stores, a lot of them use what would be a pump out solenoid, and is a hugely misunderstood and missed thing on PMs and other stuff. So these pump out solenoids are generally wired. If this is an older store with EPRs, they're generally a liquid line solenoid piped around the EPR or suction stop, and it's in parallel with it. So basically, how this works is when the refrigeration output goes to call, what it does is it goes to a time delay relay. That time delay relay then has a normally closed valve going to it, and then our normally closed wire that feeds the small valve. It may be a 1/2 inch line on a, say, 2 5/8 line. So what it's going to do is it's going to time out. So for say like 5 to 10 minutes, it's going to pump out that line post defrost. And it varies. For hot gas, it may take a little bit longer depending on the line set length, but usually 5 to 8 minutes you could pump out down to suction pressure. Now, the reason you want to do this is to avoid what Brett said. You're going to have some liquid sitting in that coil, especially if you only have a suction stop. You're going to have some liquid migration in that coil. It's cold in there. That liquid's going to keep going. It's going to keep, shrinking down, filling that coil, expanding. It's going to come back and flood the rack out. Pump out solenoids help alleviate that by pumping this thing down to basically suction pressure. Yeah. And once it's pumped down, it keeps it from freaking out and just slugging the rack. Now, the other thing behind that is it also helps the post defrost spikes. So you don't want to slam a 2 5/8 suction line full of warm vapor back on and just bang on like 5 or 6 compressors, and then the rack overshoots and undershoots and overshoots, and then this, you get this almost pulling a vacuum thing. So if you could pump that thing out, you avoid all of that. You just smooth startup. It just clicks on, ready to go, and next thing you know, the coil's open, it's down to suction pressure, it's ready to roll.
One of the other things I did want to bring up, because we were talking about bringing that case down, bringing the case out of defrost. If you do just have a liquid line solenoid, the placement of that liquid line solenoid is imperative. If you were to end up having a liquid line solenoid at the case, that's where you're shutting it down, no harm, no foul. If you have a system and you shut off the liquid line solenoid at the rack and that's it, or if the EPR is not working to close, what's going to end up happening is that whole time that it's pumping down all that refrigerant, it's essentially still refrigerating. That's a problem. So if you have, if anyone's ever pumped down a system out here, and I'm sure all of you have, it takes 5, 10, 15 minutes before all that liquid from the liquid line all the way back at the rack, if you were to shut that ball valve off just by letting it pump out naturally, it takes it could take upwards of 15 minutes, right? So if you were to not have any other thing to shut off flow and you're relying strictly off that liquid line solenoid, you've essentially just shorted your full defrost of how long it takes for that whole system to pump out. So if the defrost schedule is set for 45 minutes and the liquid line solenoid is the only thing that's shutting off the damn flow, basically now you only have a defrost of 30 minutes, because for the past 15 minutes where it was trying to pump out, it was still technically refrigerating. Kev?
Yeah, that's where you're better off just retrofitting something to a suction stop. Just liquid stop, get rid of the liquid stop and retrofit it to a suction stop. You'd be way better off, give you a way better defrost. So let's talk about electric. So electric defrost, we're talking Colorado heaters, coil heaters, emulsion type heaters. So electric defrost, basic. Like you're talking walk-in freezers, walk-in coolers, cases. We're talking Colorado heaters. They could either be single-phase defrost or three-phase defrost. In the supermarket application, you're going to see a lot of three-phase defrost, just for the simple fact that we could balance the loads between three phases and pull smaller wire, run smaller breakers, run smaller distribution blocks. So electric defrost, all we're doing is we're using a resistive Colorado heater or resistive coil heater, and we are running electricity through it and letting it heat up, just like a walk-in freezer or walk-in cooler. Now, me personally, electric defrost is the way to go with walk-in coils. Like, beats hot gas hands down. Now, the reason I say this is because if a walk-in freezer ices up, I could lock that defrost on for 2.5 hours, go do something else, let that coil cook like a piece of bread in the oven, and it'll melt all the frost off it. If it's hot gas and that happens, I mean, it's going to take forever, and it's probably not going to de-ice right, and you're going to have to get in there with a hose. Now, electric defrost in frozen food cases, no. Horrible. Just ices up all the time. The ends ice up. I mean, you're going to see the ends of the coils where the TXV side is. There's never enough heater left on there from the manufacturer to get that side warm enough, so that ice starts to build over time. So that case is eventually going to ice up. I don't care how good your termination is. I mean, you could do one defrost a day like it should. You can put 2 defrosts a day in there. It's still going to ice up. It's still going to grow eventually because there's no electric defrost on that side of the cabinet. What's your thoughts on that, Brett?
So you've had way more. Honestly, I have. You've seen that problem a lot more than I have. Like that when you say that, like I've seen it happen, but not nearly as much. So I don't think I can comment on it nearly as much as what you can. You know, the only time I've seen it, and we ended up resolving it by drilling out the orifices a little bit. But like we had a rack that was original 22, and I think we converted it to 407A or whatever, and it was causing excessive frosting around the distributor tubes. And we had figured out that it was undersized, causing more of a pressure drop because of the refrigerant, and ended up drilling it out to accommodate the extra pressure drop, so we didn't have it, so you didn't have so much freezing there at the distributor tubes.
I mean, yeah, I even see it on brand new stores, like 448 stores, like brand new out the gate.
Really?
I see it. Yep. I see it on 407 stores, see it on 404 stores, less on 404 stores, but like it's all electric defrost, whether it's Hussman, Hill Phoenix, KW, it's every one of them. Eventually that frost grows across the coil. Now with walk-in coils, it happens all the time. I mean, the Bullseye store, I mean, how many times have you had a de-ice, end of a walk-in freezer coil?
That looks like a big packed thing of snow.
Yep.
Quite a few times.
Yeah. So what we do to fix that is we got custom heaters made. We got custom U-shaped heaters made to fit the cabinets. They draw like 1.5 amps, and then you never have to defrost the cabinet again. They're the greatest things in sliced bread.
What are you hooking them up to? You hooking them up to the fan circuit or what?
Nope. Defrost circuit draws an extra amp. I have never had a problem with it overamping. I mean, if you're 2 coils and you're adding 2 amps, I mean, you usually have enough safety factor in there where it's not going to be an issue. I mean,
No,
obviously check it, but like, I mean, I usually hook it right to the defrost heaters. I just figure out if it's 3-phase, I figure out which phases have the least load on them. There's always one set of phases where, I mean, it's always lower than the others, and I'll wire them in that way. I generally will use the wire if it's a Heatcraft coil and it has the wire going through for the solenoid that nobody ever uses. I'll use that. It's plenty big enough, and you just hook the heater up. I shoot 2 stainless steel straps into the top of the coil and just hang it. It's a U-shaped or a W, depending on what coil I have, and they never ice up again.
Wait a minute. Are you talking about the piece of wire that looks like a regular,
like a fan wire,
like an appliance cable or some shit?
Yep.
With the rib black cable that they use for the solenoid.
It's a 14 gauge.
No, I know. I'm not fretting that. I just thought it was funny that someone's actually using that for something other than what it's intended for.
I mean, I've never used it for a solenoid. I mean, I've never had it like actually come into play with that. So, I mean, it's perfect for mounting electric heaters in that side of the coil. I mean, we honestly, it's an easy upsell. I mean, some customers are hesitant about it, but what's it cost to de-ice 3 freezer coils with the whole ends? It's got to be easy $800-900 service call. And if you're doing that 3-4 times a year, every time you do a PM because they're iced up, because they all build ice, they don't get hot enough because there's not enough heater on the ends of the coils, because all these manufacturers keep shrinking that heater down, save a little bit of money. So, or the heater walks more toward the electrical side. I mean, those heaters move back and forth. So, I mean, having that dedicated heater on the TXV side solves all those problems.
Yeah, and do you want to talk about sensor placement, where preferably you would like to have the sensors? I can touch on that if you want.
So sensor placement, guys, I mean, everybody does this differently. All the customers do it differently. Electric defrost, if it's a coil, I like the bullseye method, which is usually the second or third fan from a TXV side, and I will mount it like 3/4 the way up on the face of the coil. So that's where I want it. I want it away from the heaters, and I want it somewhat close to the TXV side, because that's always going to be the coldest. And then generally up higher is going to be the coldest part of the coil, because remember, if you mount it down too low, you got the pan heater. So you're going to pick up some of that radiant heat from the pan heater, but you want it up on the coil. I generally will strap it with a stainless steel zip tie to the coil face around the tube. That's how I do it. What about you, Brett?
Well, no, same thing. I mean, I keep it about three passes down, and that's a random number. Basically you want to keep it not in parallel with the defrost heater. As everyone knows here, the defrost heaters are typically on the back end side of the coil, right? And where the defrost termination is basically, on the fan side of the coil down. Wherever you're putting that defrost termination sensor, you want to make sure that it's not directly in parallel with the heater. So if you have a heater an inch down from the top, and then you have a 3-inch gap, and then you have another heater down, you want to make sure whatever pass that you pick is not, in line with the defrost heater, because that's going to do 2 things. One, you're not going to get the radiant heat from it coming, the heat coming from the back of the coil directly to the front. I also like the, strapping it down to the first pass, because no matter if you have high superheat or low superheat, that is going to be the coldest part of the coil, right? That's essentially going to be your saturation temperature at that first pass. So no matter if you have a little bit of refrigerant feeding it because you're running high superheat, because of lack of refrigerant, that place is always going to ice up no matter what. If you end up putting it closer to the suction end of the coil, you've already boiled off of that refrigerant, so you might not have nearly as much frost as you would on the inlet there. Like I said, that way it's going to be the coldest part of the coil. And that's what we're trying to do. Also, not having it all the way to the tippy top of the coil is good, not only because it's not in line with the defrost heater, but the heat is going to generally rise from, like you said, the pan heater anyway, which essentially might give that defrost termination sensor a bad reading. So yes, I fully agree with you as far as the bullseye method in order to accomplish that.
Yeah, I mean, that's generally where I like to have it. Now, if we have had some instances with low profile coils, and what I've been doing with those is they always seem to ice up on the TXV side first. So what I've been doing with those is strapping the term sensor to the TXV distributor and insulating it. And it generally will give you a slightly longer defrost time, and it'll allow that coil in to get warm enough where it'll melt off that frost and that side of the coil and keep it from defrosting or keep it from icing up.
Yeah, well, I was going to say one of the other things, the reason why that happens is if you're talking about the low profile, like the bone heatcraft evaporators, right? Usually those are put on, the areas where we don't want to take out a lot of humidity, meat boxes, right? Because if you're low, moving that velocity across there a little bit slower, you're not, sucking out all the moisture out of that product, right? Keeping that meat heavy, so they can make money on it, obviously. What I have noticed is when, if they're running it off a low temp rack, you'll see, where one side as the TXV side, that'll have frost on it. The other side of the coil won't have shit on it. And coincidentally, that is always the side every single time where the manufacturer decides to mount the defrost termination sensor. They put it on the adjacent coil to the left, opposite of your expansion valve. So it's looking for, let's just say a 55 degree termination temperature, right? And as it's heating up, has no frost on it, that part heats up first. The other side of the coil, where it did definitely have liquid flowing to it, obviously is at a lower temperature, and so that side starts icing up. And that's what I've predominantly seen. So moving that sensor over to the side of the evaporator coil that feeds all the liquid first is a good play. You will see the distributors on those are typically on the side, which they're not supposed to be, but I'm assuming they do it just because of a lack of room in there. So what ends up happening is if you have not enough liquid being distributed, whether it be the superheat is too high for that coil. I mean, typically medium temp coils are supposed to be, 6 to 8 degrees of superheat. The only anomaly with that are low profile evaporators and coffin cases. Those are the only ones that break the typical rule of being a medium temp superheat, right? You need to make sure those coils are evenly flooded. They work better that way. You have a little bit of lower TD and you'll have more even frost pattern with having it running that way. And that's why that those particular low profile coils, don't always feed all the liquid that they can, because if they don't have a good liquid supply getting fed to them, the refrigerant's going to follow the path of least resistance. Typically the lower distributor tubes, typically on the bone evaporators, they'll have like 10 distributor tubes, 5 going on the one side, 5 going on the other. The 5 going to the side of the expansion valve or on the bottom, hence why that side of the coil, no matter what, always ices up. Path of least resistance. Kev?
Yeah, I mean, those low profile coils are a pain. They've gotten even worse in the CO2 stores, where we're regulating temp with the EV and we're starving the living shit out of them. They've been a nightmare. So, I mean, that's a whole nother, bridge to cross. But so let's go into, did we talk about hot gas termination?
We did not. We were working our way up. Go ahead.
So hot gas, guys, same as cool gas, except we're using hot gas defrost. We're using the straight discharge gas off of the compressors on an HFO or HCFC. And we're either using a liquid differential valve or a discharge differential valve. They both accomplish the same thing. Me personally, I would much rather see a discharge differential valve. I think it gives you a more steady rack control and a more steady receiver than a liquid differential valve. So a discharge differential valve is creating a differential on your discharge line. So the inlet to it is going to be 20 to 30 pounds higher than the outlet. Now, I mean, you are raising your compression ratio when you do this, and you are, costing a little bit of energy. But I mean, I think the benefits wear out. They'll pay off way more than a liquid differential valve. A liquid differential valve is creating a differential from your receiver to your liquid header. Now, I mean, you could both use them for hot gas defrost. I mean, me personally, I would much rather see a discharge differential valve. A liquid differential valve is going to cause liquid to back up in the receiver. So at times it's going to give you erratic liquid levels, which me personally, I would like to see, steady, constant liquid levels.
Yeah, but why? But that's the thing. Like that's usually amount. Like I understand. Like when you go into cool gas defrost, like or when you have the liquid differential, it does go up anywhere from like 15 to 20% typically when it does go into a defrost. But a lot of times
15 to 20%. It's like most of the time I see like 70%.
Well, yeah, but there's a reason for that. There's a fucking reason for that. So my theory is, which it makes sense, liquid going in, because what are we doing? We're putting cool gas into the suction, right? That gas going into the suction is going to condense and turn into a liquid. Would you agree?
Yes.
Okay, so as that is turning into a liquid, you have liquid in that pipe. If that liquid isn't in the pipe and it's causing resistance, right? Liquid going through a pipe has more resistance than vapor. So what'll happen is, as the case gets up to, if the gas going in is the same temperature going out, that means that we're not picking up any more, energy from the coil. That also means that the gas is going to sail through that coil a hell of a lot faster than what it typically would. But the problem is that an OLDR is stupid. All it knows is I'm supposed to create a differential. So if it starts losing its differential because we're throwing through so much gas through there and not condensing into a liquid, which is not slowing down the gas, essentially what ends up happening is the OLDR, like I said, is stupid. So its immediate response is, oh, I'm losing the differential. I need to clamp down more. As it clamps down more, then that's when, because it's on the outlet of your receiver, it causes refrigerant to back up. So typically it's a defrost termination issue when you have that situation going, when you have this erratic high liquid level. We get them all the time on some of the bullseyes. One time, but one of the things that we saw, you can either have it because of defrost termination sensor is not accurate, where it's reading higher, than what it is. So that's one thing. The other thing that could be causing that is the defrost termination temperature. Think about it this way, right? If you have a saturated condensing temperature in the wintertime of 75 degrees, right? Typically on a normal rack, coming out of the drain leg, you'll get, 5 degrees of subcooling going on. Maybe it's a little bit cooler. So maybe you'll get, let's keep it at 70. Let's just say they have the defrost termination set for 70 degrees. Well, if your temperature of your cool gas coming from your drain leg that's sitting in your receiver is only 65 degrees, we can never accomplish the 70-degree termination temperature. So at that point, because it still thinks it wants to defrost, so we're still shoving in gas, but there's no more energy to basically convert that vapor to a liquid, and then in turn causing that OLDR to clamp down, which causes your erratic liquid levels.
I'll buy it to a point, but I've seen it happen at the beginning of defrost. I've seen it happen 5 minutes into defrost. I mean, you're backing up that liquid, you're going to make it unstable. Like it just happens. I mean, you're closing down the liquid line and creating that differential. You're going to back liquid up there, and depending on how big of coils you're doing, I mean, it could be drastic. Like it could be, shoot the liquid level up 70%. But I will agree, without termination, it makes it extremely erratic, and not being able to float the head down makes it even more erratic. So, I mean, I'm not a big fan of OLDRs. I would much rather have a DDR valve. It's going to give you a much smoother proper defrost. And you just eliminate the receiver hunting issues.
Yeah,
so,
but the same thing that happens with the OLDR because of, defrost going too long because of a faulty sensor or whatever can happen on the other end too, right? I mean, if you have your
you're not going to stack in a receiver though. You're not going to.
But you're going to cause excessive higher pressures during defrost,
correct.
right?
Your head pressure is going to be, say, 20 pounds higher than it normally would. So I mean, but it's going to stay 20 pounds higher. I mean, the receiver's not, slamming all over the place. I mean, it is what it is. It's a 20-pound higher. You're using more kW that way, but I mean, if you're doing it right in the middle of the night, then you shouldn't be having that much of an impact on the system. But like me personally, I hate OLDRs. I don't want them on the liquid side. Like I would much rather have a defrost differential valve. Now, with the defrost with this, we're flowing gas backwards. So we're going hot gas down the suction. We're injecting it from a solenoid. We're going hot gas down the suction. We're coming through the coil backwards. We're going through the coil. We're going through all the passes, and we're coming back through a check valve around the TXV. So piped around the TXV through the auxiliary side connector. If you have a distributor, through the auxiliary side connector, you have a check valve that allows you to bypass the TXV and the distributor. These auxiliary side connectors are imperative for cool gas and hot gas defrost because you have a distributor orifice inside of a TXV. You need to bypass that distributor orifice. That distributor orifice is extremely restrictive. Some of them are the size of a ballpoint pen tip. So you're never going to flow enough hot gas or cool gas defrost through there. So what we're doing is we're bypassing that completely. So they move it backwards and then allow the hot gas / liquid. So it's going to be liquid as it's coming out. Goes right through the distributor tubes, around through the auxiliary side connector, through the check valve, back in the liquid line, and then back to the liquid header to wait its turn to go back to the system. So it is extremely imperative to have the defrost termination sensor in the correct place. I generally like to have it just before the check valve and insulated. Right, you got anything to add to that?
No, I'm good with that. I also like using that I kind of use that sometimes as a diagnostic tool to see if like an expansion valve is set too far down, too far low.
You could see it because I mean you'll see a term sensor like if it's relatively close. I mean you'll see a term sensor reading -25, and you're like, okay. In that case is -15. The other ones are -10. That case is probably feeding a little hard.
But it's good to know that. It's good to know little tricks like that because then it helps your diagnostic process, go down because you're looking at them like, wow, that case is all the way down to, -15. The other two are at -10. You can't really figure out why. You don't know if it's the problem with the two cases that are not low enough or if it's the, problem with the case that is running too low. And coincidentally, like you said, utilizing the defrost term sensor to see what it is, we can do that off of the energy management system to see what that sensor is reading.
The people in my hotel room next to me are apparently fighting, so there's that in the background.
Fighting or the other one?
This sounds like they're fighting.
Well, if they're doing the other one, whenever they're done,
I'm not in the best area, so
I'm just saying, like, it would be funny just be like, finish him.
I don't because I don't want to be an accessory to murder. But guys, I think that's going to be a wrap on Defrost for tonight. Thanks for listening.
Thanks, guys.